So, last class we are discussing about the interior point method. That means, if you have a linear programming problem or the convex optimization problem, we can solve by using interior point method. What is this method is there? First, you have to guess one point inside the feasible region, and then we start the process, iterative process. So, if you see this, we have considered a simple example, minimize this function, that function is linear function subject to equality and inequality constants. In this case, all are inequality constants. Then if you represent that problem in graphically, we will see this is the feasible region. If you see, this one is the feasible region, and we have taken initial, if you take the initial point A here, whose coordinates is 1.5 and 1.5, that means these are the equidistance from the coordinate axis. Another point I have shown it, take this is the point B whose coordinates are 3, 1. This is the off center point. If you start the process with B point, off center point, then you will see we are moving towards the one side of the wall. Agree? So, we are in turn we are on the outside on the border of this interior point, what is called feasible region. It is not an interior point on the border of the feasible point. To avoid that one, what we did it, if you see this one, we have made a one simple transformation. That transformation is called affine transformations, means linear transformation. So, that in transform coordinate system, the coordinates are in the equidistance from the coordinate axis. So, that we have shown it how to select the, that is transform system matrix, how to select it. We have considered the transform system coordinate y1 0, y2 0. Then what is the initial and original coordinate axis, what is the x1 0, that we are dividing with that element. If you divide by this element, similarly here, then in transform system that value will be 1, that is what we have shown it. And that means, in transform systems, in transform coordinates, the our initial interior point is equidistant from the two coordinate axes, that we have seen. Now, we will see more general. If you see in transform system, now you see our point is here, B point now transformed into a new coordinate axis 1 1 point, that is equidistance from y1 axis and y2 axis, they are in equidistance 1 1 point. In general, now we will show it how to proceed that one. So, first we consider the scaling of a what is called standard LP problem, how to do. Then after doing scaling, then we will, that means in other words, how to select the transformation matrix in new coordinate axis. So, the scaling, the standard LP problem. So, standard LP problem, if you recollect, whatever the LP problem is given, we have to convert into standard LP problem first. So, our standard LP problem is minimize f of x, which is nothing but a C transpose x, whose dimension, if we consider n cross 1, then subject to A into x is equal to B. B is the number of equality constant. Even in original problem, if there is a inequality constant is there, then we know how to convert into a equality constant by introducing slack variable, surplus variable and artificial variable. So, we know these things. So, where B is the standard LP problem is B is greater than equal to 0 and x is greater than equal to, each element of x is greater than equal to 0. So, this is our standard LP problem. Let x superscript 0, whose dimension n cross 1 is the initial feasible interior point, to center this point, and this point we are considering it is off centered. That means, its distance from the coordinate axes are not equal each. So, we consider how to center x 0 defined as, to center x 0 we defined as x 0 is equal to d y of 0. Y of 0 means that coordinates systems. So, this transformation we have used. Next question is, what should be the choice of D? That D will select D like this way, x of 0, that if you consider the how many elements of x of 0 are there, n elements. So, each element of 0 2 0 dot dot x n 0. So, this is the choice of our transformation matrix, which will convert the coordinate x, that initial what is called interior point in the feasible region, it will convert into a what is called transform system equivalent what is called the interior point. So, if you see this one, and this is called the scaling matrix or transformation matrix. So, if you look at this one now, what is y 0? Then you take the transpose of that one, agree? Y 0 of this one is nothing but a d inverse. You have to take inverse of d inverse x of 0. And what is d inverse? You see, d inverse is nothing but a 1 by x 1 0, because it is a diagonal matrix, and reciprocal inverse of this one reciprocal of each diagonal element. So, this then 1 by x 2 of superscript 0, and this way 1 by x n superscript 0. So, this is our d multiplied by x 0, x 0 is x 1 superscript, x 2 superscript 0, and dot dot x n superscript 0. So, if you multiply by this thing, you will see in coordinate system the points will be 1 1 1 dot dot last element is 1. This indicates that in coordinate axis, that all the new point in coordinate axis are equidistant from each axis, and they are in one distance. Y 1 coordinates is the distance is 1 from this one. So, that point in coordinate axis point is equidistant from each axis. So, it is now centered point in that transform what is called axis. So, you can write it, this implies the unit distance from each coordinate axis, So, this transformation is called linear transformation, because they are related with a linear expressions, that sometimes it is called affine transformations or affine scaling transformation. So, now what is the scaled LP problem? Original problem was that one. Now, we have made transformation. Now, we will say what is our scaled LP problem. The scaled LP problem, now we are considering the scaled LP problem. Now, the scale LP problem is minimize f of x. Now, x I will express in terms of transform coordinates f of y is equal to C transpose. Original objective function was C transpose x, but x is now you see is related with y, new coordinate systems is dy. In place of x I have written dy. So, it is nothing but a C transpose dy, which I can write it, if you see, it is nothing but a d C whole transpose into y. That means, we know the properties of product of matrices and whole transpose, we can write it in reverse order each matrices transposes. Since D is diagonal matrix, so we do not need it for to write here D transpose. So, let us call this DC I denoted by small p, and DC if you see, it is a vector, and DC transpose is a row vector and DC is a column vector. So, that DC this into y. So, where P is equal to DC, and the dimension you can say that this dimension is n row 1 column and this dimension is n by n. So, this P dimension will be n cross 1. Okay. So, this is the now transform coordinate system. Our objective function is equivalently I can write for original system objective function equivalent in transform domain P transpose y. Y is the transform coordinates and P is what? D into C. That means, scaling matrix multiplied by C objective function, that coefficient matrix of objective function. So, that subject to what? Subject to our Ax is equal to B, that is standard LP problem. Now, A x I have converted into the transform domain, that is our D into y is equal to our B. So, now we can write it A into D y is equal to B, then I denoted by A into D is equal to B, B into y is equal to B into capital B into y is B, and that dimension m cross 1. Okay. And y dimension, if you see the y dimension is n cross 1, here also I can n cross 1. So, and B dimension, naturally this dimension is m cross n. So, our B is where? Our B is equal to A into D and P is equal to D into C. So, keeping this thing in mind, not only this, our y is all greater than equal to 0, since the x is greater than equal to 0. In this expression, if you see that how they are related, x is greater than equal to 0 and the scaling matrix, agree, that each element is positive quantity, agree, then this, if you take inverse, this will be a greater than equal to 0, that y this. So, so with this one, our original feasible interior point, our original feasible interior point x has now become y of 0, and these coordinates are, if you see, we have seen 1 1 dot dot last is 1 and this dimension is n cross 1. This indicates we have made in transform coordinate axis our interior point at the center, means it distance from each coordinate axis are same, in this case 1 1 1. So, this is what we have seen it. Now, let us say, now our job is in transform coordinate system from y0 we have to move in such a direction, so that we can achieve two objectives. One objective is to, you have to move in such a direction, one objective is it should be in the interior point, that after movement is made it, then that point, new point must be in the interior point, I think in the feasible region. Next is that point must be, that point should be such that objective function value should reduce compared to the earlier values. So, two objectives we have to meet. So, to improve y 0 with respect to f of y, we need one, a feasible solution or feasible direction, one first objective. Second is we need a decent direction. So, this objective we have to form. So, if you see, if you do for two dimensional case, if you say if this is our feasible region, let us call this is our feasible region. Now, y 0 is this one, we have to move from here in such a direction, agree, then our vector coordinates are of this one is here, agree, this y of 0, this is y of 0, this is y of 1, and it should be in the feasible region. This is the feasible region. And not only this, the function value at y is equal to y 0 on the transformed coordinates axis. What is the function value? And that function value must decrease from this value. So, two objectives we have to achieve, and for that one we have to see which direction we will move it, such that both the objectives are satisfied. To achieve this one, what we are doing it here, first we will to achieve above objectives. What we did, we considered a what is called projection matrix. Consider a projection matrix with the knowledge of our equality constraint in transform domain. An equality constraint is b y is equal to small b. With the knowledge of B matrix, we will form a what is called projection matrix, and that projection matrix, this projection matrix T is defined as I minus B transpose, then B transpose whole inverse into B. And this dimension, if you see this one, the dimension of B is m cross n, and if you proceed this one, this dimension is T dimension n cross 1. So, with the knowledge of B matrix in the equality constraints of our transform coordinate system, then we form the what is called projection matrix. This projection matrix indicates that if you multiply it by this by B, the results is 0, and this projection matrix, in addition to this projected what is called the projection matrix, this projection matrix has some properties. One can easily verify that properties. So, one property is there that T transpose is equal to T. Now, look at this one. If you take the transpose of this one, then it will be nothing but a same matrix, you will get it. It is easy to prove from the structure of that T. Next is that what you will do, just put the value of T, they take the transpose of this one. This is one property, and second property is T square is nothing but a T. How will you prove this one? Proof of second one is easy to check. You multiply T into T, and T is what? I minus B transpose B of B transpose whole inverse into B. So, that you multiplied by I minus B transpose B of B transpose whole inverse, agree, then multiplied by B. So, if you expand this one, ultimately you will get it I minus B, B of B transpose whole inverse B. So, kindly expand this one and prove yourself this is equal to this. So, there are two properties are there for projection matrix. Now, I told you I have to find out the direction in such a way, so that our new point from y0 to y1, let us call new point, that y1 point must be in the interior of the feasible region, interior point. Second, the direction what will go get it the new point, that new point function value, objective function value must be less than the previous objective function value at y is equal to y0 of y superscript 0. So, these two objective value. So, our choice of this one, let our direction vector choice n cross n is equal to t into w, t dimension n cross n, w connection n, and w is any vector of dimension n cross 1. This is any vector dimension. And so, when it is any vector, the d is any directions. Okay? So, now see this one, what will be become, to become d, to become d as a feasible direction, in other words, to be a interior point of the feasible region d, then see this one d has to satisfy this condition, that b into, let us call our new point old plus lambda some scalar which value is greater than 0 multiplied by d. That is our, that means, if you think of in two dimensional case, we are here now y0, we moved some other d, d is in these directions, and that quantity is lambda into d, and our new coordinates, when new point is that one, which is your y of this, and this must satisfy our equality constraints, that is our b. Now, let us call b y0 is equal to lambda is a scalar quantity, I can take it anywhere in the second term, this equal to b, and this, since y0 was the interior point, that it must satisfy our constant. So, this value is our b. So, this b cancelled. So, our things is coming that ultimately this boils down to beta is equal to b into d is equal to 0, since lambda is greater than 0. Okay? Any scalar quantity, this positive quantity, that means, from there d direction is there in this direction, you just multiply them. So, this condition, if it is satisfied, b into d, if it is 0, agree, b into d is it is 0, it means that our new point belongs to the in the feasible region, mean interior point. So, our d choice is here, once you selected the our projection matrix, w can be any matrix, because now see why it is any matrix. Now, you see b into d, d is what we have selected, t into w, and w is a vector, any direction vector, this vector. So, let us call it is nothing but a b into t into w, and what is b, this, and what is t, I am writing I minus b t of b t transpose whole inverse into b into w. So, if you expand that one, it will be b minus b multiplied by 0. For any value of vector, this results is 0. Agree? Only the condition is there, if you see our that B matrix, what we have A and D, that must be a full rank, that is the only conditions, then this inversion is exist. So, this is the, so our condition is B into D, B is formed if it is 0 indicates the direction D should be in such a direction, so that B into D is equal to 0. Then that means we moved from initial point to another point which is also in the interior point of this our transform coordinates, interior point in the transform coordinates. So, this is our direction we got it. Now, what is the guarantee that we have moved in that from y0 to y1 in the direction of D? That is no doubt it is a, we can prove if it is this equal to 0, B into D is 0, we proved that it is an interior point, but there is no guarantee that what is called objective function value you will get what is the objective function value you will get less than the previous objective function value at y is equal to y0. So, in order to ensure that one, what we did, you see this one. Now, next is your say to make second achievement, to make a steepest descent direction to make a steepest we select W vector. Previously we told W is any vector, but it will satisfy that our if we move any direction, it will be inside the our interior region. But now question is how to get that value of new point which will give you the objective function value less than the previous value of our previous point, okay, that value of the objective function value. So, if we select W is equal to minus P, let us see what will be our cost function values. We know our cost function, objective function in what is called coordinate system, objective function value is what? P transpose, what is this? Y, agree? And that value, if it is descending, that value must be less than equal to P transpose Y of 0, agree? Now, let us call P transpose Y is we moved from Y0 to Y1. So, it is a Y0 plus lambda into D, and that objective function value must be less than P transpose Y0. Now, you expand this one Y P transpose Y0 plus lambda P transpose D is less than P transpose Y0. So, this cancel. So, this implies that P transpose D is must be less than 0. So, if this is the descent direction, means objective function value will decrease if we move from y0 to new point y1, that objective function value will decrease provided this condition is satisfied. Now, since lambda is greater than 0. So, this condition is satisfied when if we choose W is equal to minus P, then it is obvious that P transpose D will be less than 0 P, and D we have, if we choose D is what? If you see TW, D you have some direction of D we have considered. Now, I am telling if you select the W instead of any direction, now I am telling W is equal to minus W is I am selected minus of P, okay. W I am selecting minus of P, you see here minus P. If you select it this, that minus P, this one, okay. So, it will be coming now P transpose T, W minus P, and minus is going, I take it minus here, then P. Just now exploiting the stretch, what is called properties of T. T I can write T square, because T square is equal to T into P. So, I am written now, I am writing this one T into P, there are also T into P whole transpose minus. So, this and this is what, if you see this one, this is our vector of dimension n row 1 column. This will be a whole thing will be 1 row n column. So, it is nothing but a Euclidean norm of the vector p into t square, and this quantity is always greater than equal to 0. When this is preceded with minus, so this indicate with the choice of p is equal to what is called w is equal to minus p, that we are getting with the choice of d is equal to t minus p, d is equal to t minus p, we are achieving the two objectives simultaneously. One is feasible direction we are moving, another is the objective function new point, the objective function value at the new point value is less than the objective function value at y is equal to that earlier point. That means, in the y of 0 is less, that ensures. So, therefore, the direction vector d is equal to minus T p is a feasible direction, and also a descent direction as well. So, what is our, in short, that means if the original problem is given, if it is off centered is there, you transform this into a new coordinate axis by selecting the what is called the scaling matrix. After you reach to the what is called coordinate, what is a new coordinate system, then you select from your starting point of y 0, you move in such a direction, and that direction is d is equal to minus T p, and p is the nothing but a coefficient of transform coordinate system objective function coefficient matrix or coefficient vector, this one p, and t is formed with the knowledge of B matrix, which is called projection matrix. If you select this one, d is equal to minus T p, we will simultaneously achieve both the objectives. So, this is, now let us take one simple example and see. Now, before that we will see what should be the choice of our lambda, what should be our choice of that means, in d direction how far we will move from y of 0 to what length in the direction of d we will move it. So, lambda will decide the what length. So, how to choice of d. Now, look at this expression, y is new point is, we will get it with the knowledge of initial point plus lambda into d, where lambda is greater than equal to 0, and our d, where our choice of d is equal to minus T into p, and this choice will satisfy both the objectives, will satisfy what will satisfy equality constant in transformed coordinate axis b y is equal to small b, this will satisfy one. Another condition is what will satisfy, P transpose y will be less than equal to P transpose y 0, sorry, superscript 0, this both the condition will satisfy this one. Now, let us see what is mean this one. If you see this one, y is equal to y 0 of lambda d, and in our what is called transform coordinate system, our LP problems, that means scaled LP problem, you will see the y values will be greater than equal to 0, y value is greater than equal to 0. Since y 0 is greater than equal to 0, lambda is positive quantity. So, we have a two choice on L. If if d element of the elements of D, if it is a positive, then the let us call ith element of D is positive, then it ensures the ith element of new point also positive. Now, question is, if the ith element of D is negative, then we may get the difference, even though y0 is positive, lambda is positive, but ith element of D is negative. If it is negative, the these two difference of these two we can get negative, but that depends on the choice of lambda, and we can make the choice of lambda so that in that situation the ith element of y must be positive or greater than equal to 0. So, let us see that since you can write it, since y0 sorry y of 0 is feasible, that means y j, jth component of y j is greater than equal to 0 for all j. This implies feasible, means this implies. Now, there are two situations I have considered. First situation is, if dj of 0 is all are greater than equal to 0, this then yj will be greater than equal to 0 since lambda is greater than 0. This is straightforward. There are two second situation, if dj 0 is less than equal to 0, then yj, since lambda is positive, yj, jth element of yj can be negative or positive depending upon the choice of lambda. So, we are now keeping the choice of what is called lambda should be made, so that we can get that y jth component of y is positive. Then you can write it yj 0 plus lambda j dj 0, what we want, greater than 0. If this is less than 0, this we want greater than 0. Now, both sides you have multiplied by minus, that you know yj 0 value is what, positive, and that value after scaling that transformation, and in what is called in transform coordinate axis, this value is, if you see, is nothing but a 1. So, yj both side I am multiplying by minus. So, it is a lambda j dj of 0 is less than equal to 0. So, now you can write it that one minus lambda j dj superscript 0 is equal to yj 0. So, lambda j is equal to less than equal to yj 0 minus dj 0. Now, you see the dj 0 is negative, negative and negative positive. This is already positive quantity and it is greater than 0. So, this quantity lambda is positive quantity. Now, we have a how many components of y and dj we have? We have a n components, j is equal to 1, 2, 3 this. When any one of the component of dj is positive, we ignore, we do not need it, because the sum of y0, sum of this one will be, sum of this one will be always positive. If dj is 0 or positive, then this will be always 0. So, when dj is positive quantity, then we do not consider, we ignore this. If it is a negative, then see this one. Now, I am choosing that what is the value of lambda, then lambda max is equal to minimum of lambda j superscript 0 less than 0 for negative value of lambda. Agree? See, this ratio will be minimum, which case it will be minimum. And that we will consider lambda max, because this value is positive and this value is dj value is negative, positive, negative, positive. So, this ratio which that dj component, let us call in d vector there are 5 components are there, is negative. Out of this which one is minimum, this ratio, because this minus this ratio will be positive, which one is minimum, that we will consider as a lambda max, and this will ensure that y of yj will be always greater than equal to 0. Again, this ensure this will be greater than equal to 0. So, now the remarks I am writing. Can you tell me when it will be the 0? Yj will be 0 when? Because I am taking the minimum of this one, which case it is the minimum. Let us call fifth position of dj, j is equal to 5, this is I got it minimum, agree, and corresponding that yj element will be 0, because it will be cancelling that one. Lambda j value is this one multiplied by dj, jth component 5, jth component 5 denominator cancelled, agree, this will be cancelled. Then what is called, it is same as your yj 0, that means it will be cancelled, ultimately it will be 0. So, our remarks is that if we choose lambda is equal to lambda max as minimum of delta j superscript 0 less than 0, that is negative, for negative quantity only, jth component of d is equal to yj 0 divided by minus dj 0, and this value is 1 indicates this. Then 1, at least 1 will be 0 in yj component, at least 1, it may be more than 1 or 2 variables will be 0. If it is 0, our new point will no longer be at interior point, because it is boundary on the feasible region, it will be boundary on the feasible region, but it is not in the interior point of the feasible region. So, you can write it, and the new point will no longer be an interior point. So, that is why, because I told you it will be a 0, because if you take lambda is in this way, lambda max as like this way. So, what to avoid that problems, because at least one will be 0, when one coordinate axis value will be coordinates of y will be 0, that means it is on the boundary, then y is 0 means it is on the boundary. Then what to avoid that one, what we did it, we whatever the lambda max will get it, to avoid that situation, you multiplied by this thing by a 0.9 to 0.95, within this range you make it. If you multiply by lambda max with 0.9 to 0.95, then corresponding that element will not become 0. That is our main aim. Before it reaching to the optimal point, it will not be 0. So, to avoid that one, we select lambda is equal to lambda max as lambda max is equal to, or you see we select lambda, ultimately lambda as lambda is equal to 0.9295 multiplied by lambda max. What is the lambda max? We got it here, lambda max as this one, that you multiplied by 0.9295 and then you consider that is the our step length in the direction of D will move, and that will or overcome that problem. That means that no component of y, new point y will be 0. That means it will not reach to the boundary point of this region. So, if you look at this one, our major competition burden to compute that one, I minus B, B into B transpose whole inverse B. This is the major competition involved in this process. Let us call we solve the same problem what we have considered earlier. I am briefly and quickly I will solve these problems. Refer our earlier problem we have considered. Minimize f of x is equal to minus x1 plus x2 and subject to this is equal to minus 1 1 that x1 x2 and our subject to x1 plus x2 is less than equal to 5, then x2 is equal to less than equal to 4 and x1 x2 is greater than equal to 4. So, it is our LP problem, but it is not a standard LP problem. So, you have to convert first the standard LP problem this. So, solution convert into standard LP problem. Okay. So, without much discussion, it is a we have discussed. So, standard LP problem minimize minus x1 plus x2 and it is our minus 1, if you say 1 x1 and x2, okay, and subject to we have to convert into a equality constant. So, this quantity is less than 5, that means we have to add an what is called slack variables. Let us call we added slack variables is x3 is equal to 5 and in this case x4 x2 plus x4 is equal to 4. So, our x1 x2 x3 and x4 is greater than equal to 0. Okay. So, this has now converted into our standard LP problems. Okay. So, now we identify which one is our A, B and C. So, if you see our A matrix from these two equation I can write it A matrix. Quickly I am writing that A coefficient of x1 is a this 0, coefficient of x4 is 0 there and then this is 0 1, coefficient of x2 is 1 and coefficient of x3 is 0, then this is 1. This is A matrix, this is B matrix is 5 4. Okay. And our C matrix is what? You see this our C matrix x1 x2 coefficient, x3 4 coefficient is 0, x4 coefficient is 0. So, we will write it minus 1 1, that is I am writing 0 0. So, this is our C matrix. Okay. So, our basic step, if you recollect this one, that first you convert into a what is called our what is the our initial coordinates was there. If you see the our earlier problem, we have considered the point B is our coordinates, point B coordinates in x and x1 and x2 coordinates of the original problem. B coordinates was 3 1 and it is off centered. So, what you have to do then iteration, before starting iterations, what you have to see it the our initial interior point, our how many coordinates are points are there. Here we have a 4 coordinates are there, x1 x2 x3 x4. So, initial interior point given as, or you have to find out as. Now, I know 3 1, x is x superscript 3 is 3 1. What is x 3 and x 4? We have to select x 3 and x 4 in such a way it satisfies the equality constants. Agree? So, in order to check the equality constant, you are say a into x of superscript is equal to, our case is 5 and 4. So, first equation you see here, the first equation x 1 is minus 3 and x 1 is your, sorry, x 1 is 3, x 2 is 1, x 3 must be 1, then only it will be 5, x 4 0. So, our things is that is 1, for the time I can make it x 4 0, but here you see come to this point x 2 is what 1, but I have to get it right inside 4, then x 4 must be 3, then only 1 plus 3 will be 4. So, our this will be 3. So, this is our the initial guess which satisfies our equality constant, that you have to check first. Okay. Once you get it that one, then you first see what is the objective function value at x is equal to x interior point of that one. This is our interior point, we have verified. If you consider how you have selected this one, just we have mentioned it this one. So, this equal to this value, if you put it C transpose into x of superscript 0, if you put the value of C minus 1 1 0 0 and x 0 is 3 1 1 3, if you multiply it by this, it is a minus 2. So, our at this interior point the objective function value is minus 2. So, what we have to do it next? We have to transform, and our new transformation is now transformations, coordinate of transformations. Then our x of 0 you say is equal to d y of 0, and you know what is y of 0? Y of 0 is our d inverse x of 0. What is our d? If you remember, our d is what? 3 1 1 3. This all other elements, this D matrix is 4 by 4, all other elements is D. So, D inverse will be 1 by 3, 1 1 1 by 3. So, you multiply it by this value will be all 1 1 1 1. So, it is now centered in new coordinate axis, it is in centered, means that point is that new point y 0 is equidistant from all coordinate axes. So, now see this one the scaled problem, the scaled LP problem now. What is this scaled LP problem? F of y is equal to, if we have done it these things, dc whole transpose into y, dc is p transpose y, and subject to if you say a into dy is equal to b, and this is I consider b into y is equal to small b. Now, let us compute what is p. P is d into c, and d you know it is a 3 1 1 3 multiplied by c. C is what? Minus 1 1 0 0. If you multiply it by this is a diagonal matrix, other elements are 0. If you multiply it by this, I will get it minus 3, then this 1, this and this. If you multiply it by this, you will get 0. You multiply it by this, you will get it 0. So, our P matrix is minus 3 1 0 0. Okay? Because I need the information of P in order to get the what is called directional vector, and B is what? D into C. So, you put this value of D, sorry, this is A into D. So, A matrix is what? 1 1 1 0 0 1 0 1 and D matrix is 3 1 1 3. So, all other elements is 0. If you multiply it by this, I will get the matrix 2 row 4 columns 3 1 1 0 then 0 1 0 3. Just multiply this one. So, this is our matrix. B matrix is this one, which is in transform coordinate axis B matrix equality constant we will got it this one. So, now what is our y coordinates? Y coordinate is D inverse, that is we have calculated or no? I think you have calculated here. We have calculated that y inverse is this is what we have calculated. We need not to do once again in this. So, now let us see in the transform coordinate axis what is the function value f of y is nothing but a p transpose of y. Agree? P value just now we have calculated value of p. If you see the value of p, what we calculated? Minus 3, p transpose p is this one is a minus 3 1 0 0. Then y values what we got it? The y value we got it, if you say y of 0 value what we got it? 1 1 1 1. So, we will see this value is minus 2, but it is same as our original problem we get it. So, once you check the original value, now what is our p our directional vector d, if we choose minus t into p, then this direction it will satisfy simultaneously two conditions. One is the feasible direction it will go, and not only that, the function value, that objective function value will be less than the previous objective function value. Agree? So, this what is t? T is nothing but a, if you see I minus b transpose b into b transpose whole inverse b, this is our t, into p. So, you put the values of d, b you know, p you know, you will get the directional vectors for this one. So, I will continue the next class after this. Okay.